the Association of Energy Engineers, UK chapter.
Good day, everyone. Thank you for joining today's technical webinar, the third for this year for the UK AEE, Association of Energy Engineers. So today we have Scott Birchall and we have Tim Skell from ABB giving us a deep dive into how VSDs can optimize cooling systems, and they'll also dive a bit deeper into sub-metering and energy tracking. So, time permitting, we'll also dive into Q&A. So with that, I'm going to hand over to Scott.
Tim Skell. We're sharing a laptop here. Figured it'd be easier, so we're going to split this presentation into two parts. So just kind of a quick introduction of ourselves here. So we'll start from there. So Tim Skell, Global HVACR Application Engineering Manager at ABB. I've been in drives pretty much my entire career. So graduated back in 2003. Started in drives then, worked at a couple different drive manufacturers, been at ABB for the last 13 years. And in my always had a little bit of involvement in HVAC through the years, but the last 13 that I've been at ABB, I've been dedicated as a HVAC application engineer. So worked my way up from application engineer up to application engineering manager. So we got a team of 7 app engineers that I'm responsible for the US and global. And with that, I will slide over here and let Scott introduce himself.
Yeah, so my name's Scott Birchall. I'm a global region application engineer focusing on Europe. I work as part of Tim's global team, and I'm currently in the US working with the team over here for a 2-year assignment as part of the applications team. But I primarily started off as a controls engineer when I graduated from college. Did some design and project management before joining ABB in 2017 as a HVAC sales specialist. Then I did some work with OEM teams and the sales manager for OEM in 2019 for a few years, and I moved on to this role. So I've been in engineering stroke drives for pretty much all my working life as well. So interesting to see some of the questions we get today as well.
And sliding back over to me in charge now. So you probably noticed me and Scott have a little different accents with this presentation being sponsored by the UK AE. It made sense for Scott having that UK background to be able to provide more of a local flavor for you guys, along with being able to provide some examples or answer any questions that are a little more applicable to you. Where I'm based out of the United States, so I know HVAC, but he has that little bit more of a local flavor for you. Again, also thanking UK for sponsoring us or having this presentation. They found me out on LinkedIn. I like to use LinkedIn as a kind of an educational tool, and they saw us out there sharing what I like to call Fun Fact Fridays. I post on Friday, so by all means, if you're interested, if you participate on LinkedIn, reach out to me, Tim Skell, and connect, and we can also communicate after this call. But for that, now let's get into the fun techie things here. So what are we going to do today? So I'll do a quick brief introduction into VSDs. I'll probably slip up and call them a VFD a time or two for my US background, but variable speed drive. So a quick overview on that. Then get into some of the energy metering capabilities of the drives and some of the cool calculators. So drives, a lot of people know what drives do, but they don't know about some of the really handy tools that are built in that are essentially free to utilize. You just have to know they're there. We'll talk about some tools for estimating energy savings, some calculators. And then what I'm going to do is I'm going to pass it over to Scott, where he's going to talk about some new installations and how drives and really specifically motor technology impact energy efficiency, along with how you want to handle existing solutions. So if you have an existing building and you want to look at having energy upgrades, energy efficiency improvements, what you can do. And then you'll wrap up with case studies and more importantly, some energy audits on practically what we can do to go into a building and figure out, hey, this is how you find items you want to target for energy savings and putting drives on them. So starting out with a drive, it's pretty simple on a high level. You take your line voltage, so your 400 volts, 50 hertz, something fixed, and the drive takes that and manipulates it, turns it into DC and chops it back up and makes an AC-like waveform that adjusts the voltage and the frequency of the motor, and that's how we control the speed of the motor. So my background, electrical engineering, so you're not going to get away with me talking about a little bit of schematics. So I get excited over things like diodes, capacitors, and IGBTs. So bear with me, all you mechanical guys out there. Don't worry, I'll get this done in less than a minute. But just showing you that magic that goes on inside of a drive. You've got your fixed voltage. We're just showing a single phase here, but realistically it's 3-phase. So I got my 400 volts, 50 hertz coming in, 6 diodes that rectifies it to DC. So I've got capacitors here. So these are my diodes here. Then it hits the capacitors and it smooths that out to a nice DC. Then I got my 6 IGBTs that chop this DC up into an AC-like waveform. They'll call that pulse width modulation. One of the reasons I like to show this is also for all the people who are involved in installations. Every once in a while, I'll see installations where they've got their 24-volt DC or their 0 to 10-volt analog signal run right next to the motor wires, or they might have safety wires. Maybe it's a vibration switch on a cooling tower run near the motor wires. And in practice, it looks fine, but if you actually understand what's going on under the hood there, you've got 540 volts being turned on and off 4,000 times a second. Yeah, it's not really good to put that next to your 24-volt wire. That's how you help induce noise and cause problems. So that's kind of why I like to show what's underneath the hood there. So why do we want to use VFDs? Well, we use VFDs. One of the reasons is for flow control. We look at our HVAC systems. They're designed for the coldest days in the winter. I got up this morning. It's minus 10 C here in Wisconsin, and the wind chill is going to make it a lot worse. Wave to my boys who are at the corner waiting for the bus to pick them up, and they're all sitting there looking like icicles. But we have to design the system for days that are a lot colder than today, for those coldest days. We also have to design our HVAC systems for those hottest days in the summer. You got the most humidity in middle of July, and it's very hot and humid, and your building's at full occupancy. You need to make sure your building can keep people relatively cool. But other than that, other than those extreme cases, your HVAC system is really going to be oversized. And other than just sizing for the most extreme cases, there's also some human factors that go into here. So here's an example from a spec that on a job where it basically said, oh yeah, you size your equipment, but we also want that motor to be sized because of concerns of dirty filters, size that motor 30% larger than necessary. So really all that was needed was a 6.5 kilowatt equivalent load for motor, but the motor ended up getting bumped up to an 11 kilowatt motor. So you can see it's just that human nature of trying to oversize and make things robust. Things get really, really oversized. So it's important for us to be able to back things off based on what the really system need is. And that's where drives come into play. So by having the drive, you can slow down pumps, you can slow down the fans, you save energy. We'll talk about the affinity laws very briefly in a little bit. Occupant comfort is also improved. You don't have things on, off, so you can maintain that nice steady temperature. Also, with drives, you get natural benefits. So air handlers that are starting direct across the line, when they pull in, all of a sudden you might hear a belt squeal. It puts a lot of wear and tear on that equipment. So with drives, there's a natural soft starting capability where we can ramp that motor up nice and slowly, so that way it's not as much mechanical wear and tear. Also, it's going to eliminate the inrush spikes of current. I've seen it before where air handlers kick in and all of a sudden the lights dim for a half a second because of that voltage sag. So those are all things that don't happen when you have a drive. So other than the basic comfort, variable speed capability, energy savings, there's also those fringe benefits by having variable speed drives on applications. So I mentioned energy savings, so that's where the affinity laws come in. So there's 3 main ones there. So your airflow is directly proportional to speed. So I look at this graph right down here. This is 0 to 50 hertz. So this is my speed on the bottom. And then here's my percent, either flow, torque, or power, depending which variable we're talking about. So if I'm going with respect to speed, if I cut my speed in half, my CFM is also in half. I suppose I should have changed this to something other than cubic feet per minute for this presentation, shouldn't I? So you're seeing the American, yes, I let that one slip by there. Next one is the torque. So your torque is and also pressure is proportional to the square of the speed. And then what's really important for this conversation, energy saving, is your power as far as the affinity laws. So your power is proportional to the cube of the speed. So let's take a look at an example here. So it's at full speed, 50 hertz, I'd be at 100% power and 100% airflow. But my system's oversized. I don't need it for the day. So my system says, you know what? I'm good at half flow right now. So let's take a look at that. At half flow, which is this point right here, if I go down and follow this down to my power, I'm only at 12.5% power. So considerable energy savings by able to slow things down, and it's a cube of the speed. Now, it's not exactly this perfect. I mean, unless you're a professor at a university who likes to just teach things based on formulas, they're going to say it's 12.5% power. Realistically, there's other variables. Motors are a little bit less efficient at partial speeds. Pumps have your best efficiency points of where they're going to operate. So it's not exact 12.5% power, but it gives you an order of magnitude of roughly of what you're going to be saving by slowing things down. So now I want to transition a little bit into some of the secrets that are in VSDs. There you go. I slipped up for the very first time, called it a VFD instead of a VSD, and talk about the metering capabilities of the drive. So what you see right here is a partial one-line diagram. Don't worry, you don't have to read all this little fine little font here. But what I want to do is, this is actually the building I'm in right now. So I got the main transformer here from the utility. Here's my main switch gear up top. And I blew everything away except for my mechanical room. So I have the mechanical room feeds off of this breaker here and feeds off of this breaker here. So this is all my mechanical equipment. So these are a lot of pumps. These are a lot of fans. These are all my rooftop units right here. My chilled water pumps, my hot water pumps, my condenser water pumps, my relief fans. That's what these loads all represent. So brand spanking new building we're in. So of course, if we want to know about metering, want to know about power. So you're going to have a lot of metering. So I've got my transformer here. I immediately have a meter right here. I have a very nice meter right here for basically my entire building. And then I've got another meter right here that takes care of half of my mechanical equipment. And then my other half of my mechanical room equipment is off this breaker right here, which also has a meter. So I've got a meter here, I've got a meter here, I got a meter here. Hey, it sounds really good on paper, right? But then when I actually want to get down into what I consider sub-metering and really understanding, how does this air handler compare to this air handler? How does this chilled water pump compare to this other chilled water pump? That type of data, often you don't get, because that now requires you to add a meter at every single one of these loads, and you have to integrate into that. You have to run additional wires. There's a lot of cost to that. So you don't really get the sub-metering you'd like in a lot of cases, especially my side of the world in commercial HVAC. Those things get value engineered because there's a cost aspect to it. But luckily, these pieces of equipment, almost every single one of those have a VSD on them. So let's talk about what I can get out of the VSD that a lot of people don't realize. But again, like I said, people put a drive on it. I get energy savings. I can speed it up. I can slow it down. I can control flow. But you're not using the full value of a drive. And the things I'm going to talk about, these screenshots are coming from an ABB drive, because that's just the drives I've got, and that's where I'm employed. But I'm not really sharing things that are unique to ABB. This type of concept is also available whether you've got brand A, brand B, or brand C drives. This isn't one brand or another. So this is drives in general. So first thing you can do is you can read instantaneous kilowatt. So I can see the typical drive, that's not going to be input kilowatts. That's actually going to be output kilowatts to the motor. But if you added 3% of it to it for the losses of the drive, that'll give you roughly what the input kilowatts are. Some drives are known as active front end drives, ultra low harmonic drives. They can actually give you grid input power also. But you can get that input power. You can display it on the drive. You can integrate to it via Modbus or BACnet, and then you can trend that in the building automation system. I can also look at kilowatts or megawatts. So right here, screenshot, I can see that this particular drive has consumed 3.355 megawatts of power since it's been installed, which this particular drive has probably only been operating for about 6 months because this is a new building. So what these are really nice is I can read information from the drive. I can read that daily if I want, and then I can record that through my building automation system, and I can rewrite it back to 0, and then I can record it the next day after 24 hours. I can do it weekly. I can do it monthly and then reset these counters. I don't have to reset them at all. There's a lot of different strategies there. So you as a facilities manager, energy analyst, depending on what your situation and your role is, you can really configure this up to however you want it. But the key is integrating it with your building automation system so you can read that information over BACnet or Modbus. There's amplitude loggers in there, so I can even see if I didn't have something integrated. I can even take a look and see, hey, how often is this drive running at 60 to 70% load versus 70 to 80% load? This is a screenshot of one that I took on Monday of our geothermal condenser water pump. So I can see that this particular pump is quite oversized, and typically it is at less than 50% current capacity. So perfect example of equipment being oversized. So one thing I want to point out with this metering is this is not meant to be revenue grade metering, meaning you're not supposed to bill somebody for it. So if you're a large commercial facility and you want to bill different clients based on an air handler that feeds their floor or their office, the accuracy is not there. So these are going to be better, 5% or better. Revenue grade meters are a lot of times like 0.5% accuracy, just depending on the particular meter and what part of the world you're in. What these meters are really for, though, is learning about what power is being used in the building and where it's being used. So understanding, hey, is my power being used on the air handlers, pumps? And then on top of that is comparing like equipment. So if I got two air handlers that are same size that feed very similar areas, but I see one air handler has the drive drawing 20% more power than the other air handler, I want to go investigate, why is this air handler drawing 20% more power? Is there a problem with the filters and they never got changed out like they're supposed to? Is there something going wrong with the sensor? Are my duct static pressure set points different between the two and I didn't realize it? What is going on different between these? So it allows you to compare like equipment to each other. Also, if you set up trends and you look at this, you can watch your equipment over time. So I can look at, hey, this air handler in July of last year consumed this amount of kilowatt hours. What about July this year? How much did it consume? So you can look at those type of trends and you can look for things that if it's trending in the wrong direction, you want to go ahead and investigate that. So you can look at equipment performance over the time. You compare equipment with each other, and also just get a better idea where your power is being consumed in your building. Because now instead of just saying, hey, I can see my office consumes this much and my mechanical room consumes this much power. Now it's not just my mechanical room consumes this much power. My chiller consumes this much. My hot water pumps consume this much. My chilled water pumps, my condenser water pumps, my exhaust fans, my relief fans, my supply fans. You can really see that granularity. And with that data, now you can start to make smart decisions and evaluate, hey, okay, what can I possibly do to reduce my energy bill? If you don't know where your energy is being used, you can't really reduce your energy bill. And that's one of the neat things that Scott is going to talk about when he gets into the energy audits. And again, I can't stress it enough. It's incredibly important to make sure this gets integrated into the building management system, energy management system, whatever you want to call it. If you're not pulling the data, now you're manually walking around and pulling this data off the drive's control panel, which you can do, but it's a lot more cumbersome and it's a lot less sustainable long term. And then one last thing I'd like to also share is if you have a drive that has a graphical control panel, you can also trend these things and set up trends on the drive. So this one just happens to be a 60-minute trend, but I could set this up as a 15-minute trend. I can set it up as a 24-hour trend. So I can get little mini building automation systems right in the drive to be able to trend that information and display it, but it's just not as powerful as truly integrating it into your automation system. So the previous slide, I was talking about the metering capability. We also have calculators built into a lot of drives that are out there. So we're looking at the same type of things. We start out by looking at those kilowatts and then, okay, what can we get from that? So the drive is smart enough to say, you know what, I know the affinity laws. I know how much power a motor across the line would be consuming, but because I'm slowing it down, I can give you an estimate of how much energy you're really saving by using a drive there. So the things you can save or calculate is money. So whatever units you want to be, euros, dollars, whatever. But the drive is only as smart as the commissioning agent. So the drive does not know what your energy rate is. This particular screenshot I took was still left at the factory default of 10 cents per kilowatt hour. Nobody's paying 10 cents per kilowatt hour a whole lot anymore. So that's why you see this top line and this bottom line being pretty much one significant digit separate, where the decimal point is there, is because the cost per kilowatt hour is set for 10 cents on this particular drive. But either way, this drive, compared to just running that motor full speed, has saved over $14,000 or $1,400 in its 6-month lifespan, which is pretty good for only 6 months. So, but again, it's only as good as the person who commissions it. I can show you how much power, like I just showed up here, how much power I saved. But an important commissioning task there is I talked about how drives and motors, specifically the motors, are typically oversized in HVAC. So what we want to do is tell the drive how much power that motor would consume at full speed, so I can ramp the drive up to 50 hertz in full speed and record that data and let the drive know. Otherwise, we're just assuming the worst case factory default that motor is 100% loaded when it's across the line. Realistically, we know it's going to be less than 100% because that motor was most likely oversized. So again, it's just fine tuning some of the parameters in the drive. So there's commissioning tasks associated with this. Then there's the environmental. So you can see the CO2 reduction by putting a drive on there. So these are things as people talk about sustainability and really bring these out to your operator workstations, your energy management systems. It's not just showing the status, but now you can actually show, hey, this is how much energy, money, and my carbon footprint impact I'm improving by having a drive on this equipment, bringing these out into graphics. I will say and you can pull that data out over BACnet from the drive, for example. Some people have looked pretty good to their bosses by having those extra pieces of data brought out to their drives. Like, oh yeah, remember when I told you to put a drive on this piece of equipment? Look how much it saved us. And they can keep pointing that out over the weeks, months, and years. But again, you got to commission the drive, right? You got to let it know what the CO2 conversion factor is, your metric tons per megawatt hour. Because if I got solar versus natural gas versus nuclear, those all have different factors in there. So you got to let the drive know which type of power you've got. I do have QR codes up in the top corner. So this presentation is being recorded, so you can scan those. The QR code on this one will take you to a tech note talking about the savings calculator. It's actually a tech note that Scott here wrote. The previous page also had a QR code that can take you to information. So again, check out those QR codes if you want to see additional documentation. You can see the recording of this. So last item I want to go over before I pass it over to Scott is going to be tools for estimating energy savings. So Scott's going to get into a full-blown energy appraisal and kind of show you what the executive summary of that looks like. What these tools here are kind of some of the things that go on behind the scenes, but they're also tools that are available to the public for anybody to go into. And they allow you to kind of get a good quick estimate of, hey, does it make sense to throw a VSD on this application that didn't have a VSD before for energy saving purposes? So I took some screenshots here. These are actually from the ABB website. I didn't trust my internet connection while doing this live, so I did screenshots here. But this QR code here would take you to the web page where this particular calculator is at. And again, there are multiple VSD manufacturers that have tools like this. I'm just happen to be sharing the ABB one because that's the one I know and love. So it's going to ask me to pick my application. So is that a fan, pump? There's also an option for a compressor. So after I do that, I chose fan. So there's a basic and advanced. I'm going to go through basic here, but advanced allows me to put even more data in. I can say, hey, here's what I'm doing today. I got an outlet damper. Maybe that's what's controlling my flow. Maybe I got inlet guide vanes on my air handler. Maybe that's controlling my flow. So you let it know, what do I have for my flow control today? I put in my motor power. I put in what efficiency my motor is, whether that's an IE1, IE2, IE3. We'll get in that in a little bit. Fan type, fan impeller, if I know that data. Then I go in and I enter the total number of hours this thing's going to be operating every year. And then the biggest and most important part of data that nobody ever has is what does that load curve look like? So how often am I at 100% flow? How often am I at 90% flow? How often am I at 80% flow? On the previous, in the very beginning of this, if you chose basic or advanced, if you go in advanced, you can actually get down granular and enter all that data. Unfortunately, it's very hard to have that information unless you're trending sensor information. So a lot of folks will use a generic bell curve that's common to HVAC. So that's what I'm going to use for my default here. And then you put your energy price in down here. And after you do that, it's going to spit out a report. And the report will do something like this. It'll kind of recap what I had put in there for all my different variables, kind of shows me my energy consumption being used over that bell curve. And most importantly, as far as if I'm trying to figure out how much am I going to be saving, I've got my saved megawatt hours. I've got how much I'm using today, how much I'd be using with the drive. So the delta here is my saved amount, the percentage I'm saving, how much money I'm saving, which is incredibly important when it comes to return on investment. Because a lot of times if you're 5, 6, 7 years ROI, that's not as likely of a project to get done as if you're 1 or 2 years on your ROI, return on investment. And of course, your CO2 reduction there. So very nice output report that it'll give you an idea. Hey, does it make sense for me to put a drive on this particular application that didn't have a drive in the past? And last tool I want to talk about is our Eco Design tool. So again, QR code up in the top right corner of that'll take you to this tool if you need to check it out. So when you look at motors, the original motors, the least efficient motors out there, considered IE1, your standard efficiency motors. Then they go IE2, IE3, IE4, IE5. There really should be an IE6 class now with how efficient motors have gotten. So every time you bump up a band in the IE rating, you have 10% losses in your motor as far as your watt loss. Basically, it's your heat being produced gets reduced by 10%. So one of the things you need to look at is say, you know what? I've got this application. I've got this pump that's 25 years old. This has been a great motor. I changed out the bearings once, and this motor just keeps on running. I don't need to worry about it. It just keeps on running, right? Well, maybe you want to consider replacing that motor with one that's more modern and energy efficient. So that's what this next tool is going to do. So you go to this Eco Design page and basically go ahead and click on this motor button right here. And you have kind of two options. If it's an ABB motor, you're in luck. You got less button presses. You just type in the part number and it'll pull up that motor's results immediately. If it's not an ABB motor, don't worry. What you can do is put in the general information about that about that motor, voltage, speed, the IE class, and really important is the power. And then it'll come up with an ABB motor that's really close to that existing motor, and then you can select it. And then it'll go ahead and give you some data on that motor. So what it does is it tells you how efficient that motor is. So basically at full speed, that motor is 93.3% efficient. If I'm looking at it, there's all these different load points here. There's an industry standard. That's why these load points were selected. This isn't just ABB picking load points. There's an industry standard that we went with. So in HVAC, a common load point would be 50% speed, 25% torque. So I can now see that motor is only 88.8% efficient. I can see my actual losses coming out of that motor also here. So now if I want to look at doing this with a more efficient motor, I can do that same exercise where I select the motor. And now my more efficient motor I can see is 96.3% efficient. And at that half flow point, it's 94.9. So if I put those two side by side, now I can sit there and do some rough math on how much energy I would save by simply upgrading the motor. So not even talking about the drive. Obviously, if it's got a drive on it, upgrading the drive to a newer drive is probably not going to make a big difference. You only really need to upgrade to a newer drive is if that new motor you want to go with is a type that the old drive doesn't support. There's newer motor technologies out there that Scott will get into that you want to have a modern drive on it that has the motor control algorithms for it and not a drive from 25 years ago that wouldn't know how to run that particular motor. But again, I can compare this old motor to the new motor. So I got my old motor here to my new motor. I can see the watt difference at these different load points. I can estimate how often it runs at these different load points. I can do the math and just get a ballpark on what my return on investment would be. So I've got the first tool was talking about adding a drive in the first place when there was no drive. This one talks about upgrading my motor when I had an older motor to maybe an IE2 motor to an IE5 motor. So with that, I'm going to pass her over to Scott, and then we'll open it up at the end for any questions and answers. So I won't go anywhere.
So what I'm going to start looking at is energy efficient solutions for new installations. So basically, if you are looking at a new installation for any part of your plant or building, you're considering what to install and how to go about it, that kind of thing. So I like this picture. It's kind of a little bit wacky, but it kind of gives a good analogy for what I'm going to talk about, which you've got to consider with a new installation. It's more than any just one piece. So the overall system is what matters rather than any singular piece within that system. So for example, this car, you see this F1 car, it's got a nice carbon fiber body. It's got all the aerodynamics. Everything's really great. You know, it's probably really fast, but the wheels are not really optimal for that system at all for the car. It's not really going to help it at all for what this car is designed for, and that's going to impact on its efficiency, its speed, and everything else. So you can have a really great system with loads of good parts, but if you've got a couple of pieces within that system that aren't optimal, then that can drag the whole system down, and that's something that's really got to be considered when you're looking at a new installation. So I'm going to start with a comparison on technologies, and I'm going to focus on fans because that's something that seems to have evolved a lot over the last 10 to 15 years at least. And some of the different types, if you were looking at a new installation now, some of the different types that would probably end up being considered or being looked at. So if we start on the left, we've got the ECM fan, which is an all-in-one unit with the motor and the drive all combined to the back of the fan, which is quite compact, but again, it has its pros and cons like all these do. So these came around probably, I think they started around 2003, something like that. You see them in a lot of smaller size HVAC applications, for example. But again, they've got limitations on airflow in terms of the pressure they can achieve and the flows that they can achieve. So we'll touch a bit more on that as we go on. You've also got the IMD, which is the integrated motor drive. So this is like a small skid type assembly where the drive again is generally mounted to the motor. The big difference for this compared to the ECM is you can generally specify what type of motor you would like on this skid. So you've got more flexibility in terms of the type of motor. So if you've got certain types of motor on your plant already, you could specify that to come. So obviously you've got spurs across plant and it makes things easier. It's something you're familiar with. You can also evolve with the latest motor technology. As Tim mentioned, we're up to IE6, and I'll touch a bit more upon that in the coming slides. And then you've got the discrete drive and motor package where the fan is generally installed with the motor and then the drive is separate controlling the fan, which again has its pros and cons. There's a lot more flexibility in this option than the other two. Replacing and servicing parts is much easier with this option than the other two. But you've got to consider the pros and cons, which we're going to move on to on the next few slides. So one of the big things as well that drives a lot of this is the motor technology, because the motor is what is going to consume the most energy on plant, and it's something that's very important. But as I mentioned back at the start, the whole system's got to be considered. So these are the motors that are sort of we're going to look at. So generally, in the past, you'd be looking at an induction motor. They've been around for many years, and I'd say up until around 10, 15 years ago, everything that came to site or got installed was pretty much an induction motor. But in the push for efficiency, manufacturers such as ABB and many others have developed technology to try and push the efficiency further. And as you can see, these bands, as Tim touched upon, the IE3, IE5 and all that, it's each band, as Tim mentioned, I'll touch on it again, 10% less losses than the last one. But I would preface that and say, don't just look at the band because it is only a band. Because you could have two IE5, for example, and one could be at the top of the band, one could be at the bottom of the band. And also these bands are looking at as well. These bands are obviously looking at based on full speed as well. You've got to consider how your system's operating, and optimized for that as well, because some of these motors will run really efficient at the top end of the curve and maybe not so efficient further down the curve. So you've got to look at these things and consider these when installing. We've got some of the benefits and limitations across these. I won't go into loads of detail on this, but it's there for reference. But as you can see, the main point to address is all the technology is pushing for higher IE ratings, and this is a good starting point for your system. Generally, if you look at an IE5 compared to an IE4, it would be more efficient, but you've got to check on the operation. If the IE5 is operating really badly and the IE4 is optimized, it could be close. So it's not a way of determining efficiency just easy off the top of a hat. So looking at drives, so obviously we've got ABB drives featured here. This is where we're from, but most top line manufacturers have got quality drives with proven technology, with all serviceable technology as well. So if anything fails with that drive, any fans or parts, you can easily replace them via a local partner or via a local ABB office. So this is the ongoing sort of support you can get as well with the drives. It's a lot easier to replace things. As Tim's touched upon, a lot of HVAC specific features, and also we've got drives for all industrial applications as well, which have equally got specific features for those industries. So a lot of the stuff that we've put into the drives for each segment is tailored towards that industry. So it's really helpful in terms of setting things up and making things easier. The good thing with the drive as well is, at least the ACH 580, the more modern drives, you can control virtually any motor. So sometimes you don't always know. I've seen in the past projects where people have some fans and motors turning up that they weren't 100% sure what type of motor it'd be. So if you've got drives ordered and they don't control a wide range of motors, then that could be an issue. The seamless integration as well is something that's easy to integrate, and as Tim touched upon a lot of the pieces as well, some of the things that you can display and some of the things that you can trend, it's just, you get a lot more information using a drive than some of the other offerings on the market. So I think for energy saving, information is key. As Tim said, if you don't know how much energy you're using or you can't track that, then how are you going to know whether something's running inefficiently? How are you going to know how much you've saved compared to what you did before? There's a lot of things there that can be useful. The reliability as well. As I mentioned, a lot of the parts are serviceable, and you'll likely get a long lifetime out of these if you service following the service plan. So there's a lot of benefits to that in terms of the longevity. So some of these other components that are all built into one units, they tend to have an issue and tend to fail a little sooner because they generally run hotter and stuff like that. So that's something to consider as well, which we'll touch upon on the coming slides. So just a quick comparison of the strengths and weaknesses for some of these technologies we just looked at. So we started with the ECM. So some of the strengths: upfront cost and ease of installation. So they're generally slightly cheaper than these other two, and they're quite easy to install. It's just four bolts to put in. Weaknesses around flexibility. So once you've installed that, you can't really overspeed. If you ever need any more flow at any point, or you need to speed up the system, there's generally quite a restriction on that because you can't really speed it up any further than what it already is. Serviceability and replacement, another big issue where generally if something fails on this unit, you've got to replace the whole unit. That's the advice, to take it out and put a new one in. So some of these other two options, you can actually replace individual parts to keep that running longer. And obviously it saves on the carbon footprint rather than taking something away and recycling it, or rather than keeping something operating for longer. So the IDM, it's got a bit more flexibility involved. So obviously you can specify the type of motor, which is pretty useful as motor technology evolves. And if you've got a certain type of motor on plant, or you've got a certain brand that you want to stick with, you can stick with that. Again, ease of installation, it will come as an all-in-one skid, so it just installs as a package kind of thing. So there's less things to consider around that. So on the IDM, so the replacement is quite difficult. Obviously, you've got to replace the full skid, so it can be sometimes difficult getting these in and out once you've initially installed it. Sometimes they're only useful for certain applications as well, so you've got to consider what you're installing it for. But I would I would say that for everything really. You've got to consider your application and look at what technology is best. So discrete drives and motors, flexibility and customization. You can use any type of motor you want, any type of drive you want. You can swap things in and out. If a certain motor manufacturer comes out with a more efficient motor, you can swap it for that. If a certain motor or drive manufacturer disappears from the market, there's plenty of others you can replace it with. So you've got that kind of that cover in terms of, and that freedom of choice. Whereas some of these other options are, once you've installed that, you're pretty much looking at like for like moving forward. Reliability, so these are a lot more serviceable in terms of you can grease the bearings on the motor, you can change parts on the drive. All these things make it much more reliable over the long term. And obviously, because they're separate, they're generally installed in a more friendly environment, away from too much heat or dust or anything like that. You can control where they're installed a lot easier. So serviceability and circularity, we touched on serviceability already, but circularity, so again, if you can keep something running for longer rather than throwing something away and wasting it, then that is something that's important for your carbon footprint, and all that kind of thing. We have actually got EPD documents. I don't know if you guys are familiar with EPDs yet, but we've got all those for our drives and motors and stuff like that. So it's something that you can put into your calculations. So the upfront cost is generally a bit more than the other two, but the long-term efficiency and the long-term benefit is they'll operate a lot longer. The total cost of ownership would be much less than the other options. The installation, obviously, you're installing things separately, so the drive and motor are separate from each other. So you've got to consider where to put things a little bit more. So I put that on that side. I think that's fair enough. So moving on, motor technology has evolved, and now we're on to IE6. ABB have just started pushing out an IE6 NRM motor, and I think there's other manufacturers around that mark as well. So this push for efficiency is seeing them bands increase. What I would say is consider all the factors impacting the system wide to wire efficiency. So what's the true system efficiency rather than just individual pieces? We've all had a new car where it claims to be, 65 mpg or something crazy. You get it home, you start operating it and using it, going shopping or taking the kids to school or anything like that, and you never get the mpg that it says in the book. And that's because that mpg has been calculated at optimal conditions. You've got to consider how it's really being used rather than what they've tested in a lab. So you've got harmonics and service and replacement of system components. We've sort of touched upon that. And what about the impact on the building owner in terms of replacement and stuff? If you can keep something running longer, whoever owns that building, whoever owns that asset, it's much easier for them to keep that thing operating and have it serviceable rather than having to replace things all the time and extra downtime and loss of production, for example. And the environmental impact as well. You've got to think about what's this application going to look like in 5-10 years time further down the line. Is it still going to be able to be operational? Are we going to be able to get parts for it and stuff like that? That's something that should be considered. And also, as I mentioned, the EPDs, what are the components made out of, where have they come from, all that kind of stuff. The EPDs cover those really well. So next we're going to look at a little comparison on some fan technology just to give you a feel for how some things have evolved over the years. So if we start on the top left there, you look, generally in the past you get a centrifugal fan for basically forever up until about 15 years ago, maybe 20. Any fan you would get would generally be a centrifugal fan and get installed, and it'd be something like this in the box there, and your ductwork could look something like that if you're looking at an AHU. So the fan itself would be around 75% efficiency. All these efficiency numbers here are all. So if you looked at the motor off the bat and said 91%, you thought, oh, my system's 91% efficient. It's not really the case. You've got to consider all these, including the belt, because a lot of these were belt driven as well. And the total efficiency was 63%. But moving on from that, as technology's evolved and people have pushed the efficiency boundaries to make things more efficient, next came the plug fan or the ECM type, where you can see as it's installed on the wall there. So you can see there's an increase in efficiency overall. No belts with these, but there is some downside, as you can see, because the actual drive and motor are in the airflow there. The actual airflow is distributed out at 90 degrees to the left and the right. So it's impacting the airflow, and it's in the airflow. And this is one of the things that reduces the lifespan of some of these fans because they're running hotter and they're actually in the airflow. So this has an impact on the efficiency. So moving on from there, plug fans came to the market, as I said, around 2003, I think. And to meet certain pressures and flow rates, they moved on to putting them into fan walls, as you can see in this top right one, where it's multiple fans all together to keep these things operating. A lot of times they'll claim it as redundancy, where if one fails, it'll pick up and all that kind of stuff. But if you do that, you got to have walls installed and isolation dampers. And we've seen a lot of these in real effect where they're not really used as a redundant system. They're just operated as they are. And if one fails, then it needs to be swapped out. So that's something to consider as well. And as you can see with these, the airflow does short circuit with each other as well because they're impacting on each other and it's going out to 90 degrees to the left and right. So there is an impact on efficiency. Now you can see it did gain a bit more efficiency compared to the single fan. So it has gone up to 70%. So again, everybody's pushing towards that. But on this case, you've got to have 4 fans installed on multiple fans. What we're seeing more recently come to the market is axial fans. And one of the OEMs that we've been working with a lot, who are sort of one of the market leaders, is Novenco. And as you can see, the axial fan is a little bit different to these other ones. You can see there's no need for a wall there or any ducting. It just operates into the open air there. And you can see the fan, motor and drive together running about 85% efficient. So it's something that we've seen recently. We've seen more fan manufacturers going down this route as well to, again, go towards that more efficient. And if you look at that system efficiency, that's 85%. So these are all important things to understand. If you look at all these individual percentage numbers, these are all good and well, but it's this total efficiency that really matters. And what you'll see if you're energy monitoring or energy logging anything, you're going to see what the impacts of the total efficiency. Really, that's what you're going to be paying on your bill. So also just a quick comparison between a couple of fan walls that was done I think it was sometime last year for a customer in Ireland who was looking at efficiency is more than just a fan as well. So total efficiency and design, wire to wire efficiency is what matters. So comparing the 2 6-fan fan walls, you're looking at the efficiency class, both IE5. So again, mentioning earlier about IE5 being a judgment for efficiency is not always a great case. It's a good starting point, but it's not something I should say. These systems are equal. So what they did is, if you look at the comparable airflow, so they're both 20,004 meters cubed per second, and then the static pressure as well, 450 pascals. So just to balance it out and to show that these are like-for-like comparisons, the pressure and flow was maintained both. So the electrical power input, you can see there's 18% reduction using the axial fan option compared to the ECM combined package. And the system total efficiency, which is again what we're really interested in, is 76.7 compared to 67%. And this is where you can really understand how efficient a system is, because these numbers don't lie. The weight as well, it was interesting to see the weight difference in terms of these fans compared to the others. They were much lighter because these are generally marketed as light and compact and easy to use. And also the dimensions as well, they proved to be smaller, which again is something you've got to consider for your application. These are all things you've got to look at when considering what you're installing and what your application is. The other interesting one is the bearing lifetime. So within the manual itself for these fans, it shows us 40,000 hours, which is that's at 40 degrees C as well. So sometimes these are running hotter than that and it can be less. So in the manual, it says you need to replace these at that time, which is difficult, which ends up being the whole unit being replaced. So the operating time for these is not really as long as you would expect. Whereas for the Novenco, you're looking at 70,000 hours. And also with the motors, you can actually service the bearings as well. So that's something you can extend if you serviced everything. So that was just a little comparison to give you a like for like. So next, I'm going to move on to energy efficient solutions for existing installations. So what have you got an existing installation and you were looking at what can I do to save energy, what can I do to upgrade? So why can you save with variable speed drives? Tim's gone into a lot of the technical side of it, understanding exactly what a drive does in order to operate and how it saves energy. Let's look at some of the facts and things out there that really make drives an interesting choice for installing. So 70% of all buildings were built before current energy codes. So a lot of buildings that have got existing equipment that need, it won't be the most efficient on the market anymore. There's opportunity for upgrade. So 90% of these buildings will still be around in 2050. So again, these are things that need to be looked at. What is it going to be like in the future? As I mentioned earlier, when you're installing something, what is this going to look like in 10 years' time? Is it still going to be serviceable and actionable? Buildings account for 45% of greenhouse gas emissions in major cities. So this is just focusing on buildings alone, never mind the industrial plants as well. So buildings have a lot of impact on cities. HVAC itself consumes about 50% of the energy in commercial buildings, so that's a lot. So it's something that should be looked at and reviewed. And a variable speed drive can save up to 60% energy, as Tim mentioned with the cube law and the stuff like that. That's going to really help you save energy if you can reduce the speed by applying a drive to a motor that's currently not got a drive installed. That's going to save a lot of energy in most cases. IE5 motors as well offer 30% reduced energy losses compared to IE2, for example. So if you're looking at older motors, so generally older buildings will have older motors. If you look at, as Tim's comparison mentioned, just upgrading the motor can make a big impact as well. Only 23% of the world's 300 million motors have drives fitted as well. So this incorporates everything, I believe. So that's a lot of motors out there that still don't have any drives fitted. Or I would imagine that 23%, some of those could be commissioned a little better as well. So it's worth looking at. And 95% of motors are oversized for the application. Tim touched upon this with the sizing for worst case. I mean, we said 95%, which is probably more. I can't see many actual applications where you can size absolutely bang on for the application. It's very difficult. So most motors need to be controlled in some way. So that's something that's got to be considered. So a couple of case studies to refer to. As Tim mentioned, this is being recorded, so something you can refer back to. So GlaxoSmithKline vaccine plant, helping them reach net zero. They installed ABB IE5 scenario motors, as you can see in this picture. So we supplied these packages. This was a plant in Hungary. The return investment was less than 2 years. So it was done with a local ABB value provider as well, which is something we'll touch upon a little bit later in terms of getting these applications installed and upgraded. Another one is IKEA in Spain. So ABB drives enhanced efficiency of IKEA stores. So as you can see, we've worked with IKEA on a lot of their stores in installing ACH 580 drives and saving energy for their stores as well. So it's something that's really interesting in terms of the payback and the ongoing efficiency achieved with these applications as well. So next, I'm going to look at typical applications good for savings. What are the ones that you should be looking for? The ones that are low-hanging fruit, the ones that you could really do something with to start with. And fans and pumps are the typical ones. So centrifugal type fans were the easiest for energy saving because of variable torque loads. As you reduce the speed, the energy savings cubed. So that's something that Tim sort of touched upon as well. A lot of traditional control methods like on-off control, well, they're not actually speed controlled at all, and they might be mechanically restricted as well by a damper or in cases of some kind of a flow restriction. So they're easy to actually savings up to 70% we've seen. You can use schedulers in VSD if you need to install it after the fact. This is a picture of a typical air handling unit, for example. Centrifugal pumps as well. Again, traditionally many different pumps in buildings and across different applications. Traditionally on-off control or valve controlled. So again, you're just pumping against a semi-closed valve. You're just burning energy really. It's not saving at all. So again, savings up to 70%. These are the easiest ones to understand and easiest ones to save with in terms of reducing the speed that you get the most return on. So next, we're going to just look at You've had a lot of good information put out there today and a lot of different things about drives and how they can help you save energy, but how can you turn it into an opportunity? How can you make it? How can you realise some savings? So what we do at ABB, and I think many other companies do the same, is we do energy appraisals. So what we generally do is we'll go to site and we'll look at different applications on site and we'll review it and put forward take some pictures and all that and put it into a report and generate some return on investment and different paybacks and carbon reduction and stuff like that. So it's a pretty simple process. No need for complicated data at this stage. You don't need any measuring equipment. It's generally done by ABB sales, service, or partners. Within our organisation, others may be different, but generally it'll be somebody who'll come to site and have a walk around with you and look at where there's potential for energy saving. The next one could be an engineered appraisal. So you can return to site or go to site and measure applications where you're really looking for proof to ensure that the energy savings are there. If it's something that might be marginal, or if it's something it's going to be a difficult install, or it's a tricky application to shut down or something like that, you might want some more peace of mind or some more convincing first. Or you may need this. We've seen this before where people need this to get the investment to actually pay for the projects and stuff like that, to convince somebody to release the funds, all that kind of stuff. So basically what this is, somebody will go to site, they'll measure the application before, and then in a lot of cases they'll install a trial drive or a higher drive where it will measure. You can obviously reduce the speed of the motor, realize the savings for the same amount of time, and then measure that as well. And then you can compare the two values and see what the savings look like. We've also seen people where they'll do this with one or two applications. If they've got multiple on site, they'll do it with one or two. If they turn out to be good, then they can do it with the rest. This will generally be done again with ABB sales, service, or partners, depending on the site and what it is. It'll be different people for each one, and depending on what industry as well. There's also people out there on the market as well who do full system analysis with guarantees. So you'll have companies who'll do this energy service where they'll come to site and they'll monitor everything and they'll look at it and they'll give you a consultative approach and they'll give you a report and they'll guarantee some energy savings at a cost and stuff like that. It's a bit of a different way of going about it, but again, they'll generally calculate and scientifically prove the savings, and then they usually take out of the savings. Some of the payback is through the savings. So if you're saving X amount, some of the project is paid for through them savings, if that makes sense. So what does a report look like, and how do we do it at ABB? So this is our tool, what we use. So if you look at this, we've got different parameters that you put in there. So you can decide whether you put in a pump or a fan and a drive, and you can add the motor in there as well. You put the nameplate power in, operating time, you put the flow cycle as well. So as Tim mentioned earlier about the bell curve and not knowing what that is, this drop down menu here, you can select bell curve, you can select PID, you can select the different options there if you don't know. If you do know exactly how it's operating, the cycle, you can put user and you can actually put in which ones you want and make it exactly how your application is. But again, it's 50-50 whether people know that information. It's not that easy unless you've already got it. It will recommend the drive for this application. You can put in a drive price and installation price. And then what happens then is you get this summary calculated on the right hand side here. So this will give you a list of all the applications that have been audited. It gives you the running costs for each one. It gives you the annual savings implementing the actual turn down that we've looked at, or just applying the drive and operating at the speed you've selected. Gives you the total investment. So what would the investment be for each one? So you put the drive and installation price in there. You've also got the energy saved as well. So the kilowatt hours cumulative across the installation, the applications that you've looked at. Also the payback time. So you've got individual payback time for each application. So as you can see, some are less than 2 years, some are around 2 years, some are higher. Again, it gives you all these individual and as a total. Sometimes people look at this as a total and say it gives you an opportunity at least to get some of these installed, because you might not, get the 8-year one, for example, passed as an energy saving project on its own. But if you put it together as a full scale investment, it looks a lot more attractive. And then CO2 saved as well. We've seen a lot more focus on CO2 saved from people as well now, even more than the payback. Some people are more interested in how much CO2 they can save compared to the payback. And I think a lot of this is down to things like the carbon net zero push. And we're seeing a lot from councils and different places like that. So it gives you the total payback at the bottom as well. So that's something that's interesting. It also gives you the carbon saved compared to like miles driven in a car. So and miles flown on a plane. So 326,000 miles on a plane. And also 9,500 energy saving light bulbs it would take to actually be the equivalent to this. Because a lot of people see energy saving and they think, let's install LED lighting. So it gives you a good comparison compared to that. So a quick summary. So touching on energy saving with variable speed drives, Tim went through that, how a drive operates and how you can save energy with a drive. Energy metering within the drive as well. So again, a real important point that Tim mentioned was, if you don't understand how much energy is being used by different applications, then how can you know where to focus your efforts? How can you know where you can make savings, and how can you know you have made savings? So there's a lot of things there that are really useful in terms of recognizing that without having to do a lot of extra work in terms of installations and sensors and monitoring and stuff like that. So practical tools for energy savings. Tim went through some of the energy saving stuff you could do ahead of time. So a lot of the tools that you can look at in terms of, do we think there's an opportunity for energy saving here? You can put some details in there quite easily and get a sort of feel for, is this worth putting some more effort into and looking at maybe an audit or looking at going further into it. Now, I touched upon new installations again. New installation, is really important to understand the system efficiency. It's okay having a couple of good pieces that are 95% efficient or whatever, but what matters is the overall system. Energy in compared to energy out. That's really what, power in, power out is what really matters, because you're putting a lot of power in and the power out isn't that great, then the efficiency ain't going to be too good either. Efficiency opportunities in outdated equipment. So there's a lot of existing applications out there. There's a lot of installations already been in situ for a long time. People think drives are installed everywhere already. Well, they're not. As we've seen, only 23% of the global motors have got drives on. And even though we've been doing this energy stuff in the UK for 15, 20 years plus, people say to us, oh yeah, we've got drives on everything, this, that, and the other. We've got it all energy efficient. We go to site and we find loads of stuff where they can improve and they've not got drives installed at all. So a lot of times there's that complacency that people have already got this stuff when they haven't. And case studies and energy audits. So just a couple of examples of where this has been successful in terms of some big companies. We've got loads of examples for virtually every industry you can think of. But in terms of case studies, we can only share ones that online actually that have been published. We have got a lot of other examples for virtually any industry you can think of as well. So no matter what your industry you're in, don't let that be a restriction. We've done it on all kinds of stuff, all industrial plants, HVAC plants, marine equipment, everything really. So there's a lot of stuff there across ABB really. And the audits itself, audits is something we've done in the UK for a long time as well, something that's been very successful. Some huge blue chip kind of arenas, for example. We've done Wembley, we've done quite a few different big sort of event spaces. We've done a lot of office blocks, we've done a lot of things. So they're really useful in terms of finding the detail of the energy saving and what can I actually save. What about my plant? Because a lot of this information is good and stuff, and it gives you an idea how you can save energy, but you've got to apply it specifically to your equipment, really. That's all, really. So from there, any questions at all?
There was one question in the chat, and I answered it, but I'll just kind of speak to it. So the question came in as far as if the logger system, so that's that amplitude logger that shows the current consumption of the motor over time, if that's available on most ABB drives, or if that was an option at installation. So I'm going to speak from the HVAC perspective because that's the product I know. It is standard. It is not an option. It comes with all the drives for the flagship drive. So it used to be the ACH 550 going 20 plus years ago to what we is the main HVAC drive now, which is ACH 580. That is standard.
Thanks, Scott and Tim, for insightful technical webinar on how and how VSDs can optimize cooling systems. I see there's a question from Bob, and that's probably one for me to answer, Bob. So yeah, what we'll do is we will publish the video online on the UKAE website probably, and post it up on LinkedIn for you to access. And so just watch out for that and on LinkedIn. Any other questions? Because I think we are running over time. But if there are any questions, please, feel free to ask before we close.
It's only 10 o'clock where me and Scott are at. We've got all day yet for questions.
No problem.
Yeah, if you do have any questions that come up after the time as well, feel free to reach out. We're pretty active on LinkedIn, and you've got most of our details as well, I think, there as well.
Okay, no questions. So I guess that's a wrap. Thank you for your time, everybody. Hope you enjoyed that technical webinar. And yes, keep a lookout for further webinars in the new year. Thank you. Take care. Bye.
Thanks, everyone.
Thanks, everybody.
The Association of Energy Engineers, UK chapter.